Well, you may be wondering why we want you to calculate percentage composition and things like that, because it doesn't seem to have like too much of an application. We looked at it for working out how much metal we might get from alumina, but really it's something that we want you to be able to do along the journey of doing something a little bit more complicated. And that little bit more complicated is being able to calculate empirical formula and molecular formula of particular compounds. Okay, so let's have a look at some definitions because we always need to have a few definitions. Okay, so we know what a chemical formula is. Okay, so something like H2O or NaCl or Na2SO4, something like that. Okay, they're chemical formulas. But chemical formulas can either be molecular formulas, which indicate the actual number and type of atoms in a molecule, so something like C6H12O6, which is glucose, okay, or they can be an empirical formula, which is the relative number or the lowest ratio of how the atoms go together in that molecule. So if we look at something like glucose, which is C6H12O6, well, the lowest ratio I could have is actually divide everything by 6, and we would actually get CH2O. Okay, so the molecular formula is the exact actual number of all the type of atoms in the molecule, whereas the empirical formula just gives us the lowest common ratio. Okay, so it's the simplest whole number ratio of atoms. Okay, so if we look at CO2, we can see that, well, in this case, the lowest whole number ratio is actually already there. I can't divide C by 2 to get a half, because that's not a whole number. So sometimes empirical formulae and molecular formulae are the same. Okay, don't get freaked out if sometimes you come to do a calculation, you work out, hey, the molecular formula and the empirical formula are the same. Check if that makes sense with all the data that you've got, and then just move on, because that can indeed be the case. Okay, but it's not always. If we look at something like C6H6, which you may remember as benzene, hopefully you remember as benzene, its empirical formula is going to be CH. Okay, so let's fill in this table. We've already shown you glucose, C6H12O6, and its empirical formula, the lowest whole number ratio, CH2O. Ethane, which is C2H6, well, I can divide these both by 2 and I get CH3. Okay, so acetylene, which is C2H2, have a go. What do you think that one's going to be? Is that its lowest whole number ratio? Nope. It's going to simplify down to CH, and then benzene, interestingly enough, will simplify down to the same empirical formula. And we'll look at why that is a little bit later on when we do our organic unit. But remember that things can have the same empirical formula, but if they have the same molecular formula, they're the same compound, unless they're put together differently. Okay, but we need to know the molecular formula versus the empirical formula. And a lot of things will have the same empirical formula but be different because the specific number of atoms is different, which is what we see here with acetylene and benzene. Okay, well, we need to be able to find the empirical formulae. This is something that we need to be able to do in order to do some of the calculations and things we do with chemistry. They're determined experimentally by using a analytical method where we can work out the percentage composition of every element in there. Okay, so you'll get a little report and it'll say it's this much nitrogen, this much carbon, this much oxygen, and you can confirm if it is indeed what you think it is. So when we have that percentage composition report, okay, and we already know that the percentage composition means the percentage of each element in our compound, we saw that in the last video, we can use that information to help us find the empirical formula. And we follow the same steps every time. So let's go through those steps, make note of these, because if you follow this process, it always works, but you have to follow it in order. Okay, so we write down the symbols of the elements present, and usually you will just keep to the order in the question. Okay. At this stage in your understanding of chemistry, you're probably not going to know which way they go together. Just keep it the way it is in the question. If it's listed carbon, hydrogen, nitrogen, then write them down that way. Okay, assume the mass of the sample is 100 grams and all percentages become grams. We saw that in the previous video. If it's a percentage, if it adds up to 100 grams, then all our percentages just swap from being percentages to grams, which is really handy. Once we've got it in grams, we can do other things with it, like find mole, which is exactly what the next step is. Number 3, convert masses to moles by using n is equal to mass divided by molar mass, MR for us. Okay. Number 4, find the simplest whole number ratio of the atoms by dividing all the numbers of moles by the smallest number of moles. This sounds really confusing, but when I show you how to set it out in a table, it should become pretty obvious. Then, if necessary, multiply by a factor to convert all the numbers to whole numbers. Now, make a note of these. We tend to only do this, we tend to round a bit with this because the numbers don't always work out. But if you see something that is 0.25, that should make you think to multiply by 4. But it has to be pretty much 0.25, not 0.27 or 0.28. It needs to be 0.25. If you see something that is 0.333 recurring, well then hopefully that will make you think to multiply by 3. So 0.333, which is 1/3. Okay, we're going to multiply by 3. So this is essentially 1/4. This is 1/3. And of course that should be getting you to think, oh, if I see a half, I want to multiply by 2. Okay. So these are the ones that we're mostly going to look out for. If you see these, you should be thinking that you need to multiply. This will become more obvious when we do one. Okay, we can put that together as a flowchart. So we find the percentage, find the mass of each in 100 grams, find the number of moles, simplest whole number ratio, and empirical formula. This is a process you need to remember. Easy thing is, it's easier to remember if we give it a go. So let's have a look at this. A compound of sulfur contains 2.4% hydrogen, 3.90% sulfur, and 58.6% oxygen. Find the empirical formula of the compound. Okay, step 1. What was step 1? Step 1 was write down the symbol of the elements present. Okay, keep to the order in the question. Can do that. So it told me that I had hydrogen, it told me I had sulfur, keep changing slide, and it said I had oxygen. So I'm going to write them down with little ratio dots in between them because I want to work out the ratio of hydrogen to sulfur to oxygen, and this reminds me of it. Okay, so we're saying hydrogen is to sulfur is to oxygen. Okay, step 2 was assume 100 grams. If I'm assuming 100 grams, the beauty is my percentages become masses. So this becomes 2.4. This becomes 39, and this one becomes 58.6. Okay, next step was to find n of each. Okay, so I'm going to find n, so I'm going to take my mass, 2.4, and divide by my molar mass. Well, the molar mass of hydrogen is 1, and the molar mass of sulfur is 32, take my word for it for now, and then the molar mass of oxygen is 16. Okay, so if I calculate all of those in terms of number of mole, things are not cooperating with me. Okay, so plug those into my calculator, I get 2.4 divided by 1. So 2.4, don't know why I put that into the calculator. 39 divided by 32 gives me 1.21875, okay, keeping all the digits at this point in time, and then 58.6 divided by 16, probably think I should be using 32.1 there, but anyway, 3.6625. Okay, so these are the mole of each of them. Now the next step was to divide everything by the smallest number of mole. That seems weird, but what we're going to do is we're going to look at these values and we're going to find the smallest one. That's this one here for sulfur. Okay, that's my smallest number of mole. So now I'm going to divide by smallest n, and that's going to be 2.4 divided by 1.21875. This is going to be divided by 1.21875, and then this one is going to be divided by 1.21875, and hopefully you see where we're going to be going here. We're going to get 2.4 divided by 1.21875. We're going to get 1.96, and then we're going to get 1, and then we're going to get 3.6625 divided by 1.21875, and we're going to get 3.00. Remember how I said to look out for 0.25, 0.333, 0.50, 1.96? It's not any of those, so we're going to round that up to 2 because it's really close. And then what I'm going to see is I'm going to get 2 is to 1 is to 3. And that's my ratio. Okay, so that's the lowest common ratio for hydrogen is to sulfur is to oxygen. So this is actually going to be H2SO3. Okay, so I've just taken this and applied it to the element from here in each column. S is 1, O is 3. I've written them in the order from my question, and that's my empirical formula. If you want it typed out all nice and neat, it's actually on your next slide. Okay, goes through exactly what we did there. Okay, and steps it out for you. Okay. So the whole number ratio, we're going to take divide by the smallest, and we get 2 is to 1 is to 3. We do 2 is to 1 is to 3. We can see we get H2S1O3. Okay, so the empirical formula is H2SO3. Have a go at doing these ones yourself. Okay, and we will go through them in class. This one can get it's just a little bit longer. Okay, remember to keep them in order. So you're going to have carbon, hydrogen, nitrogen, just nitrogen and oxygen. Set up your table as we did in the previous one. Okay, and then this one, 0.6 grams of carbon is oxidized to 2.20 grams of compound that was produced. Calculate the empirical formula. This is telling me that it was reacted with oxygen. Okay, this one's telling me that it was reacted with O2, so that means it's just going to be C and O. Okay, have a go at those ones, and I will go through some solutions with you in class for those. Next up is how we go from empirical formula to molecular formula.